Hi, this is Jayakrishnan, and let me very briefly introduce you to three main aspects of my research interest, namely my past endeavors in doing research, my current professional exposure, and my proposals and insights into future work. One of the first research problems I worked on was on the effect of spatial scales in calculating incident solar radiation. Of course, it's well known that solar radiation that reaches the Earth's surface varies across different geographic extents, but my interest was on investigating the effect on macro scales, say solar potential on household rooftops, which could be affected by various factors such as neighboring buildings and trees. In the pursuit of this research, I started mapping the buildings and trees in our university campus using existing georeference data, as well as incorporating height details for each and every entity by using total station. Though this was a little tedious, it proved to be a good starting point to calculate rooftop solar potential, as well as ancillary information such as carbon footprint savings. The carbon footprint savings calculation is based on the fact that for producing 1 unit of electricity from burning lignite, which happens to be the primary energy provider to our city, 612.5 grams of carbon dioxide is emitted. So, for every unit of clean energy produced would obviate a proportionate amount of carbon dioxide. Financial calculations were also based on a simple methodology that I developed. The workflow was also streamlined by using Model Builder. The results for our campus was encouraging enough to pursue the research further. Coupled with good GIS visualization techniques, the concept of using GIS to determine the solar potential at macro scale served the purpose effectively. Here you can see the results for our campus, where you can see the 3D models of our buildings, where the user can click a building and he can get the information of the solar potential and possible carbon dioxide savings that he can achieve by converting into solar energy. But the real breakthrough in the research work was my introduction to LiDAR. LiDAR presented a whole new set of opportunities as well as challenges. Using LiDAR meant I could use the most accurate elevation details for precisely calculating solar potential, as well as model dynamic phenomena such as flood. Such calculations could also be extended to whole cities now, but the sheer volume of data was intimidating itself. Also, standard GIS packages lacked out-of-the-box LiDAR processing capabilities. Here you can see a small script tool that I developed in Python to process and integrate LiDAR data into GIS as high-resolution DEMs on a batch mode. This facilitated processing large datasets one at a time and also automated results. Here you can see LiDAR imagery, which was derived from processing LiDAR data and by filling smaller voids. The larger voids are due to the presence of water in this area. My research turned towards a dying marshland in the city. This was coupled with increased flooding experience in the areas around the marsh. So my question was, can GIS and satellite imageries help in the conservation efforts of this marsh? Using old topo sheets and historical imageries from Google Earth, the marsh area over 2 decades was mapped. The results were obvious. Marsh area had been drastically reduced due to encroachment, as it was classified as a wasteland. Using GIS tools, I was able to demonstrate the sponge effect of the marsh, because the marsh was helping in storing the excessive flood waters over the years, and a reduction in the marsh area has directly affected the storage capacity of the marsh. The TIN models and rainfall data were used to calculate storage capacity of the marsh. That clearly explained how the reduction in storage capacity caused increased flooding in areas adjacent to the marsh. My final semester project was on using GIS to find persistent lung cancer hotspots in my city. Environmental and occupational exposures such as radiation, passive smoking, radon, asbestos and pesticides are one of the major exogenous factors causing lung cancer. The purpose of this study was to determine if there were persistent lung cancers spatial clusters of lung cancer incidents in Chennai, and to calculate the risk of an individual to develop a lung cancer complication based on the individual's current age and his or her past residence or workplaces. The latter parameter is directly influenced by these environmental and occupational exposures. GIS tools were created in ArcGIS 10 to automate the creation of lung cancer hotspots maps, and Python scripting was used to calculate a risk index. A web mapping API was used to create a web interface to display the risk index based on the user's geocoded residence or workplace location and his or her duration of stay in that place. In my current stint as a developer, I am being exposed to a variety of S3 development platforms such as ArcObjects for application development in desktop, engine and server JS. I am also involved in the development of web and mobile mapping applications using ArcGIS APIs for Flex, Silverlight and Android. During my graduate studies, I would like to take up research in some of the following areas, namely ubiquitous mapping, building prototypes of spatially intelligent appliances, natural GIS user interfaces. Of course, web and mobile GIS is in my research radar always. Let me explain one of my principal area of research interest, that is my opinion on how to achieve ubiquity in mapping platforms. This basically involves collection of spatial data from various trivial sources such as mobile phone signals, GTFS XML feeds, sensor networks, etc. Deriving useful parameters such as signal density, transportation frequency, crowd, concentration of pollutants, etc. But the real challenge is to decipher useful spatial patterns using maybe regressive statistical testing and topological or network analysis. This can lead to interesting phenomena such as characterizing traffic flows, population flows, monitor disease outbreaks, etc. And finally, the ultimate utility of such information can be realized by dynamic dissemination of data through mobile and web. Spatially intelligent appliances may be a very broad research area, but my understanding of such devices, or rather the areas where I'd like to concentrate, are on contextual intelligence, where devices can understand the context and give meaningful results. An example may be a PDA which reminds us of what to do when we reach a particular location rather than a time-based schedule. My research interests are motivated by the fact that those are cognitively challenging and had positive social implications and were robust in technological designs. Thank you for it.